Okay, everybody. Today it's going to be very different compared to the other things that I did on Twitch in the previous sessions, because today is both more technical and more about the design. The ACL log thing was a good way in order to start easy, and now I want to try to show a more deep process here on Twitch about the design of a new complex feature. So we have in Redis 6 and in the unstable branch a new feature which is called client-side caching. Client-side caching is the ability to Redis to remember which set of keys was delivered to a given client, and such client is a special client which tries to memorize the value of the keys that it requested in the past, so that the next time, instead of asking Redis again, we can use the client-side copy of such key. However, it is useful in such case that, so here we have our client, and it will remember that the key A is associated with the value 1000, and the server will remember that such client C requested the key A. So if the key A changes again because a different client performs a command like incr A in order to increment the value of A, the server can send an invalidation message to C saying invalidate key A. So the client that cached this value can destroy it, and the next time the A value will be needed again, it will be requested to the server again. That's the basic idea. However, this situation is handled in the server side like that. There is an array from 0 to a very large number, or 1 million and something, if I remember correctly, or 4 million and something. It should be 2 for 24 slots, if I remember correctly, something like that. And in each of such slots, what we do, like this is slot 3, and keys are hashed, this is the key name, in order to obtain the caching slot. So maybe the key foo will hash to cache slot 3. So 3 will contain a radix tree that maps to every client ID which may have a copy of a key in this hash slot. So when we modify some key in hash slot 3, we know just that we need to send a notification message to each of these clients in order for them to invalidate the cached keys. That's the idea. But this means that the server side here is forced to keep in memory all these informations. And if you think about many caching slots and many clients, because certain applications have like 10 key, 100 key clients, it's going to be a lot of memory. So in order to reduce memory, Redis uses a trick, which is the following. So we have many caching slots here. And what we have is a configuration parameter that tells Redis just take like a maximum fill rate of 2%. So if we start to have too many caching slots populated because clients are requesting many keys but nobody is invalidating keys writing, Redis will start to invalidate the caching slots even if there are no writes at random, in order to reach again this target. And it will send invalidation messages, but at the same time it will be possible to reclaim memory. This is a possibility, but in very low memory systems, or in general when we want to have very efficient memory usage in server side, we don't want that. So we can ask ourselves, why is this useful at all? Simply because if we have many clients and only this client asked for key A, we want to send the invalidation message only to E. This means that this is basically a space bandwidth trade-off. What we want to use more memory here and more CPU time also, because tracking this requires some CPU time, or we want instead to use a lot of network bandwidth, not remembering here who asked given keys and then sending validation messages to everybody, because we don't know which client could have the key E, this one or this one or this one. So we want also to have a feature that allows to have this kind of trade-off, more bandwidth, more messages, but no used memory at all here, almost, at least. Okay, so my first design was, my current design is that normally this is how it works basically. Okay, we can spin up Redis instance here. Sorry, I have a cold. Fuck. The client must activate this feature. Is this the wrong version? No, it's the command which is different. So let's see. How was the command name? Tracking on. Okay. This enables the client to be in tracking mode because we want to track the keys, the caching slots actually. We don't really memorize the keys, but we only memorize the caching slots of keys that the client requested. Otherwise, it's going to be very memory inefficient. And then when I ask for a key, the server will remember that this client, which is client 5, may have a copy of foo. And if I want to see what happens when I have to switch, okay, when I enable tracking, I need to do something different also. I have to redirect it to another client. So let's start a first session where we okay, basically the tracking name of the channel is Redis invalidate. Okay, this is how it works in practice using RESP 2. It works better in RESP 3, but for now we use RESP 2. So we get the client ID here and we subscribe to this channel. Then in another client, which is the client, this is basically the first client is the client we use in order to, a connection we use in order to get the invalidation messages. The second client here takes this number here of the first connection and tells client tracking on redirect to 8. So redirect the invalidation messages about this connection to the client 8. And if I ask for foo, and then from another unrelated client I set foo to another value, here I receive an invalidation message. Redis invalidate. And this is the hash slot that I invalidated. Sorry. So, what I want to do instead, I want to be able to do something like that. Client tracking on broadcast. Broadcast is the option name. That means just don't remember anything, but broadcast every invalidation message you get to me. Every invalidation message about any key touched to me. And probably I want to be able to say also pattern object, pattern, I don't know, counter. Maybe I can only cache 2 things. However, we cannot do efficient pattern matching. So anyway, the patterns will be always in that form with the asterisk at the end. So it's better to say like prefix object and prefix counter. Okay, so this is our first part of the design. We can copy and paste it. Okay, we want something like that. And another important thing is the following. We say that we never transfer the key names like foo, bar, or whatever. We send instead numbers of the caching slots. This is useful in order to reduce the memory usage, because in this way, here at top level, we can have just an array of caching slots, and we can also have a given maximum fill rate, and we can evict as we said. However, once we don't know to take this in memory, why instead don't send directly key names? to the client. This is useful for two reasons. One is that given that there is no longer trade-off here, it is useful to just make the client side more efficient. Anyway, we are not worried about the bytes consumed by the key name in the messages. The messages are large enough already, as you can see here, so it's just a matter of a few bytes. In this way, basically, the clients, this is a client with which a cached value B here, A and B here, even if those two will collide to the same caching slot, I can invalidate just this key here. However, if a client has an implementation based on caching slots, it can take the hashing of this and turn it into a caching slot number. So in order to have a single implementation for all the cases. Instead, if it's a client that wants to support just broadcasting, it will have a flat array, flat dictionary of keys, and that's all. And when an invalidation message is reached, we just kill such key from the dictionary, and it's as simple as that. So, how can this made efficient? The first thing that we don't want to do is to do all the work for many clients again and again, because in this setup I can have many clients. Given that I'm not remembering each client what's caching, such clients are more or less all the same for me. If they are so similar, I want to do the work in order to send the notification to such clients a single time. So what we could do is to have a set of radix trees, which is basically a radix tree containing all the prefixes. The prefix of the clients that didn't specify any pattern will be just this one, the empty string. And the empty string will have an object, will point to an object, which could be like a dictionary or a radix tree of all the keys that in this pattern here were touched during the current event loop cycle. So A, B, and C. And this is a linked list of clients that registered for this pattern here. So when I get a notification of a key, I try to check it against every entry in the radix tree, and for every entry every entry that matches, I will add the key here. Note that this data structure is useful only for a single event loop cycle, so we don't have memory concerns here, because every time that we return to the event loop and we send all the notifications to the clients, we will destroy all this state. So here maybe there is another pattern like object, not pattern, sorry, prefix, we said. And again, this is like a dictionary with object 2 and a list of clients. When we return from the event loop, what we do is to scan every of these patterns, and we can basically compose. So let's write this part of the specification. So okay, so far so good. This is another radix tree with the keys, and these are the clients that subscribed. Okay. Okay. Then, when we are about to return back on the event loop, we do that for each prefix we have, we create an invalidation reply that includes all the key names for it. We send such reply to every client in the list. We can throw away the CSC because state object at this point, because we send the notifications, no more work to do. Yes, this looks like it's okay from the point of view of the main design. So this requires, however, some change here. As you can see, the invalidation message is a single string, but we want a new channel like Redis bcast invalidate be invalidate that receives an array of keys. So with a single message we can send a lot of keys. And what's cool in this design is that we create an invalidation reply with all the keys, and then we can send the same reply to all the clients, even if the current Redis implementation will copy the buffer. but still it's faster because we have to scan the dictionary just one time. Then, okay, there is the memcopy for each client, but it's not a big deal. It's the same of PubSub anyway. I hope PubSub works now and is scalable enough, because memcopy is very fast. It's not like scanning the keys and sending for the first client, the second, and whatever. Yeah, this looks like a good setup. I will stream again later today, starting to implement, to refine initially this design, because we need a bit more bits, I believe, and then we'll start to implement this in Redis. Thanks for watching. See you later.